everyone, I'm Michelle. I think I'm the last TA to give a video talk, and this one is going to be for experiment number 6. So this is just an overview of experiment number 6 itself. For this particular lab, we are not going to have a lot of calculations. I don't think there's actually any actual calculations within this lab. However, there are a lot of different concepts that I do want to review and go over with you guys before you guys go into answering all of the questions. So the first one is going to be that ion formation. This consists of our electron configuration, electron dot symbol, as well as the loss and gain of electrons, as well as determination of charge of an actual ion. And we'll talk about how we actually get to those things in a minute. The next 4 are ionic compounds, metals with variable changes, polyatomic ions, and molecular compounds. For all 4 of these categories, we're going to be looking for the physical properties, formulas, as well as the naming. Now, some of these are going to be a little bit easier, the ones at the top, and the ones at the bottom might be a little bit tougher. Don't be afraid to use your resources. Go to your textbook, go to the online sources. One thing that I highly recommend is your material safety data sheets, or MSDS sheets, because that's going to allow you to get some of those physical properties as well as help you out with the formulas and the naming. Finally, we have our structures, and our structures are actually going to differ a little bit based on molecular or electronic structure, as well as what is the actual impact that a lone pair has on structure. So, with that in mind, we're going to skip to the first portion, or ion formation. So in ion formation, there's just a bunch of these different things, and I'm just going to drop this down, and don't be overwhelmed, just kind of go one at a time, and I'll try to go through it as well. So when we're talking about an element, we want to think about a substance that cannot be interconverted or broken down into a simpler substance. So hopefully you guys can see this. I have my periodic table here, and each one of these, as we know, is a periodic table of element. So if I'm looking at something like sodium, so sodium is going to be over here, and if we look at what the atomic number is for sodium, or Na, we can see that it's 11. And I'm just going to blow that up for us. So this is the number assigned to each element, and it's denoted on the periodic table. Now, for the electron configuration of this, it's going to be the distribution of electrons of an actual atom or molecule in an orbital. So I'm going to go over what sodium is in a little bit after I finish the rest of these definitions, but I wanted to just quickly take a tour of our periodic table. So we'll notice that we have kind of a couple of different blocks. We have this short block here, and helium, which is over on this side, is normally over here too. And this is what we call our S block. So we have 2 electrons, or 1, 2, that are associated with this S block in each valence shell. A valence shell, if we think about it, is the outermost shell that we're dealing with. So if we're looking at our 1s orbital, that would be our hydrogen and our helium, then that is going to mean that we have 2 valence electrons in that outermost shell. Now, normally we have 8 electrons in our outermost shell, which is why we talk about the octet rule, or fulfilling those 8 electrons. If we have something like fluorine, which is atomic number 9, we have our electrons in our s orbital, but then we also have these electrons in what we call the p orbital. So boron, carbon, nitrogen, oxygen, fluorine, and neon are all part of the p block. So we have the S, the P. This block down here are our transition metals, as you guys might know them as, is our D block. And then usually way down at the end, we have our F block. So S, P, D, and then F. And if we think about it, so we have 2 electrons associated with each s orbital. We have 1, 2, 3, 4, 5, 6 electrons associated with each p orbital. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 associated with each d, and then it increases from there. For the scope of this course, we're really going to be dealing mainly with our sp and a little bit of d block. Okay, so that is kind of just a general, what are we looking at? So when we're actually thinking about electron configuration, we want to think about what electrons are making up our element or whatever it might be. So for Na over here, we have 2 electrons in our 1s block. We have 2 electrons in our 2s. We have 6 electrons in that 2p. And then we have 1 electron in our 3s. And so that is the way that we kind of look at it through here. There is another way to think about it, and some people do find this a little bit easier. So if you draw out all of your different orbitals, so we have 1s, 2s, 3s, and then p starts at that 2p, and you guys will get a little bit more into the quantum mechanics of this a little bit later probably. We have 3p, 4p, 5p, 6p, and so forth. We're first going to fill up that 1s. So it's really how are electrons filling up our orbitals first. Then we have our electrons going into the 2s block. Then we have the 2p and then the 3s. And then the 3p and the 4s. And then the 3d, 4p, 5s. So you'll notice that we have those 3p electrons going into the 3p shell before the 4s, because the 3p, because of the 3, is actually a little bit lower in energy. And you guys will get a little bit farther into this a little bit later in the course. But this is kind of a nice way to remember those little caveats and which ones are filling up first, if you don't want to look at that periodic table of elements, which also helps us with this concept. So the next concept that we're looking at is the electron dot symbol, and this is our first part of our Lewis dot structure, or I believe the book might call it your electron configuration of an atom. Lewis dot structure is really the same idea, where we're looking at and we're putting the valence shell of the electrons around whatever that element is. We have the loss and gain of electrons, and this is really looking at that difference of electrons from the nearest valence shell. So you might have to get rid of electrons to make it a full octet, or you might have to add a couple atoms, and we'll talk about exactly what that means in a second. The next thing is our electron configuration of an ion. So this is when we have added electrons or subtracted electrons to make it a full octet. So we are naming that electron configuration with the full valence shell. Next we have the ionic charge, and this is the amount of electrons gained or lost to make the full octet, or to make that valence shell complete. We have our ion symbol, which is really a combination of our element and our ionic charge. And then we have what is our ion actually called. So I'm just going to kind of walk through a couple of examples. So our first one is going to be Na, and we talked a little bit about this before, but Na is our sodium ion. And if we're looking at this, we can kind of pull up our periodic table, and we know that sodium, well, it's not going to pull it up like I want to. Sodium is atomic number 11. When we're thinking about the electron configuration, and I'll try to put this here so you guys can see it, but I really advise you guys to follow along on your own periodic table. We know that we're going to have the 1s is going to have 2 electrons. We're going to go to the 2s, which has 2 electrons. We have the 2p, which is filled next with 6 electrons. And then we have the 3s with 1 electron, which is the one that makes it the 11 versus the 10. Now there is another way that you can do this. You can go to the fullest octet, which in this case is neon, and you can put your 3s1, and this is just an abbreviated